This video lesson will show you some other uses of the equilibrium constant, in particular doing some calculation to work to predict concentrations or to predict whether a system is at equilibrium. So first, predicting concentrations. This is some very simple algebra. In most cases, the equilibrium constant is given right there, and one concentration of a reactant or product is unknown, but the other two, for example, are. So let's take a look at this. This is decomposition of water vapor from water to hydrogen gas and oxygen gas. Looks like that's not balanced. So let's put a 2 there and a 2 there. We have balanced chemical equation. So first things first, and then rather, the equilibrium constant is given, 2.4 times 10 to the negative 3. And two of the three reactants or products are given, in this case, water vapor and hydrogen gas. The third thing is not, and that's what's going to be asked. What is the oxygen concentration at equilibrium from this balanced chemical equation? So let's write the equilibrium constant first, right? Products over reactants with coefficients as exponents. It's going to look like that. I don't know if you can see that all on the same page, right? Products over reactants, coefficients as exponents. And then remember, we know the value of the equilibrium constant. We know the value of that thing right there. And we were given the value of hydrogen gas and the value of water vapor right there. So this is simply an exercise in plug and chug. We're going to put all the numbers in that we know. All right, so there's the equilibrium constant. Here's the values of the things we know. And then solve for oxygen. That's what's done here, just rearranging and isolating variables to solve for the unknown. And then plug your numbers in and go. Watch for all the squares and do your order of operations correctly. Remember, square things first. But here's the answer. The value for oxygen is 0.0804 moles per liter. So that's an easy example. A little bit trickier when we talk about systems that aren't quite at equilibrium yet. And remember, systems take time to approach equilibrium. This is an example that we looked at earlier in class where we put these two reactants in a jar, just water vapor and carbon monoxide gas. So here's the initial conditions, and we let them react and approach equilibrium. So they get consumed, their concentration decreases as the concentration of the products increase, and eventually we reach equilibrium. Remember, equilibrium is where the forward and reverse reaction rates are the same. But until that time, the forward and reverse reactions the concentrations are changing, like in this area or in this area here. And that's what we call Q, the reaction quotient. So let me go back to this slide right here. Is this time either before or sometimes even after equilibrium has been reached, if some conditions have been changed, like temperature, that a system is not at equilibrium yet. It has the same form. We write it with products over reactants with coefficients as exponents. And what you might do in this case is you might take a sample, like or not inject rather, but put a syringe and grab a sample of these gases reacting and put it in an analytical machine like a gas chromatograph, and you can plug those numbers in for products over reactants with coefficients as exponents right here, right? So not at equilibrium yet. We kind of think of it as the reaction quotient as a snapshot of concentrations as they progress, as they approach equilibrium. But it's not going to be equal to this value of the equilibrium constant yet. So Q is a condition that's not at equilibrium yet. So this value of products over reactants with coefficients as exponents is experimentally taken as the system's approaching equilibrium, that value will not be equal to the equilibrium constant. Okay. If you do those calculations though, right, you take a sample and you find the reactant and product concentrations, you plug them into the equilibrium constant expression, and you get this, the reaction quotient is equal to the equilibrium constant, guess what? You're at equilibrium, right? And we stop referring to it as the reaction quotient, because you're at equilibrium. But there's other things that can go wrong, or not wrong, but can be different circumstances. What if the reaction quotient isn't equal to K? What if it's greater than K, or the other way it can be not equal to K is that it's less than K? What direction will the reaction shift? Well, we can tell by the value of Q, the reaction quotient, compared to K, what's this going to do? So just remember this. Both Q and K are written the same way, products over reactants, just a ratio, with coefficients as exponents, of course. So first of all, if Q is less than K, that means the products are too small, right? And you've got to make more product. So it's going to shift right. Okay. And then vice versa. If Q is bigger than K, that means you've got too much product. So it's going to shift left and create more reactant. All right. So this is a pretty good diagram of this. Take a look again. If Q is too small, you don't have enough products, it's going to shift to the right and make more product. Okay. So if Q is too big, it's going to shift left and make more reactant. And again, if Q is equal to K, then you are at equilibrium presently. So let's do a little bit of math with this work right here. Let's talk about an example. So first of all, is a decomposition of hydrogen iodide to hydrogen and iodine gases. That looks balanced. That's good. There's the equilibrium constant right there, 0.0184. So it doesn't progress to the right, make a lot of products, but it does some because the number's smaller than 1. All right. Now, this is an easy one. If the initial concentration for all those gases is 1 mole per liter, how's the reaction going to proceed? So first, write the equilibrium constant. Notice the only thing that's squared is the hydrogen iodide because of the coefficients, right? And let's put the number 1 in for all of those things. So we'll simply have 1, whoops, oh, hold on. There we go. Sorry, technical error there. Bear with me. I'm using my tablet that I haven't used in a little while. All right, so it'll be 1 times 1 over 1 squared, which is, of course, equal to 1. So the value of the the reaction quotient, Q, is 1. And it does tell us that the equilibrium constant here is 0.0184. So look, the value of the reaction quotient is much bigger than the equilibrium constant. And again, if it's too large, let me go back to this page. If it's too large, that means you've got too much product, so it's going to shift to the left and make more reactant. So let's go back to this. Once again, we calculated it was 1, so it's much larger. There's too much product, so it's going to shift to the left and make more reactant. So that's the answer to the question. How will the reaction proceed? It's going to shift to the left to make more reactant. I think I said make more product before, but it's going to shift left and make more reactant. Let's do another one. Same exact problem, but we'll do it with more complicated numbers instead of ones. So here's another. This is homogeneous equilibrium, thankfully. So it's sulfur dioxide combusting with oxygen to produce sulfur trioxide. There's the equilibrium constant, which is 5. All right, that's an easy number to remember. So is the system at equilibrium if we take a sample and we get these values right here? So you have to write an equilibrium constant based on the balanced chemical equation. Remember, coefficients as exponents, etc. That's what I wrote right here. So Q is sulfur trioxide squared, the products over the reactants with coefficients as exponents. You get the idea. So let's just plug those numbers in. I do that, and I get a value of around 4. Oh, 4 is less than 5. And if it's products over reactants, we need to make more products to get to the value of 5. So this reaction is going to shift to the right and make more product and increase that value of the reaction quotient until it gets to 5. It makes more products. Okay, good. So that's a good introduction to calculations and predictions you can do with the equilibrium constant.